Now that we've done an introduction, on this page we'll talk about how sample means vary in random samples. In this unit, we will work with quantitative variables again, which is a change from the last unit, so the statistics and parameters will be means instead of proportions. We begin this module with a discussion of the sampling distribution of sample means. Our goal is to understand how sample means vary when we select random samples from a population with a known mean. We did the same type of thinking previously with sample proportions to understand the distribution of sample proportions. Ultimately, we will develop a probability model based on the distribution of sample means. We use the probability model with an actual sample mean to test a claim about the population mean or to estimate a population mean. Either there's going to be a claim about it or we're going to estimate it if we don't know it or we have no idea, there's no claim or anything about it. So let's look at an example just to kind of make this more clear. This example is about birth weights. I think we've seen something like this before, but we'll revisit it now that we're back to talking about quantitative variables. The WHO, the World Health Organization, monitors many variables to assess a population's overall health. One of these variables is birth weight. Birth weight is a quantitative variable. We can calculate the mean birth weight for a population. Suppose that babies in a certain town had a mean birth weight of 3,500 grams or 3,500 grams in the year 2005. This year, a random sample of 9 babies has a mean birth weight of 3,400 grams in the same town. So 3,500 is the parameter from a population. We use the Greek letter mu to represent it because it's the mean. Remember, we've used mu before for mean. And it's 3,500 grams, as they said. The 3,400 is a statistic from the sample. So we'll write X with a little bar on top, the sample mean, I guess. Population mean, or with the thought population mean. That was the old population mean, but we're trying to test to see if this new sample mean is closer to a current population mean. Maybe it's changed from 2005. Sample mean. X bar, and then population mean, we'll use mu. Okay, all right. Obviously, the sample weighs less on average than the population of babies in the town. A decrease in the town's mean birth weight could indicate a decline in overall health of the town. But does the sample give strong enough evidence that the town's mean birth weight is actually less than 3,500 grams this year? I mean, we only sampled 9 babies when the town probably has a lot more than that. Oh, depending on the size of the town, maybe not. To answer this question, we need to understand how much the means from random variables vary. Would a sample be likely or unlikely to have a mean birth weight of 3,400 grams if the mean weight of all the babies is 3,500 grams? We outline this investigation in the following diagram. Okay, so we have a population. The population is babies in a town. The variable is birth weight, and the mean birth weight, mu, is 3,500. Okay, from populations with this mu, we got one actual sample. The sample mean was 3,500. And we're wondering, this is our thought here, does this fit with our other samples? Now we'll look at other random samples. A random sample with a population, one sample mean that was obtained, again, was 3,605. Maybe that came from computer simulation based on all the information from this town. Another one was 3,230, the last 3,320, et cetera, there might be more. As before, the logic of inference is the same. Begin with a population with a certain population mean, in this case, mu is 3,500, and take a random sample of 9 babies at a time. If we do that over and over and over,